Let us start this lecture with a thought process, that is, it is better not to hanker after happiness, rather try to experience it in each moment. All of us are hankering after the happiness, but it is difficult to get, but rather we should experience it in each moment, which is a part of human life. And let us recall what we learnt in the last lecture. In the last lecture, we basically started discussing about the processes involved during the atomization in a simple orifice, or which you call as a non-impinging atomizer, and we have seen that it undergoes a various processes of 4 regimes. One is Rayleigh regime, the first wind induced breakoff, and second wind induced breakoff, and then of course the atomization. And for atomization we need to have a very high pressure and also the high velocity of the jet which is required. And later on also we looked at what happens in case of a impinging atomizer when 2 liquid impinge into each other, then a liquid fan sheet being formed, and which really undergoes certain oscillations and waves will be there, which I did not show, but and that helps in disintegrating the liquid into ligaments and also the secondary atomization, that is droplets. And we have seen that and today we will be looking at various kinds of atomizer that are being developed for liquid propellant rocket engines. And as I told earlier, it will be basically divided into 2 categories. One is non-impinging atomizer, other is impinging atomizer, and several types of atomizer have been developed and used by various researchers, but we will be discussing only some of the representative atomizer under these 2 categories. And let us look at some of them. If you look at the shower head and coaxial and the Shrill are basically non-impinging atomizer, and doublet, triplet, biplanar, self-impinging and splash plate atomizer will be coming under the impinging atomizer. Keep in mind that non-impinging atomizer generally used for non-hypergolic propellant, and whereas the impinging atomizer can be used either for hypergolic propellant or non-hypergolic propellant, depending on the type of design what one should use, depending on its design. So, let us look at the shower head atomizer, and this case the orifices are being given and which shown here, and this is your fuel manifold and this is your oxidizer manifold, and of course, it is having 2 orifices or the holes, these are orifices, and the liquid jets are coming out of these orifices, and keep in mind that the liquid jets retain its identity for a longer length of the combustion chamber. And this is shower head is similar to that of the shower what we use for every day for taking bath, and this will be straight holes which will be or orifice being placed such that the straight liquid jets are being devised by these shower heads, and they will not really interact much in the vicinity of the shower head, and rather they will be interacting, and then also the spray will be formed little downstream, a little away from the face of the shower head atomizer. And as a result that mixing and also the vaporization will be taking place away from the shower head, and that is one way is good, so that it will not really block the things, but however the length of the combustor will be higher, and that is why that is not being used, although it was used in the very beginning by the famous V2 liquid propellant rocket engine designed by German around Second World War. The advantage of the shower head atomizer is that it is acting like a shield between the combustion chamber wall and also the combustion zone, such that the heat transfer from the flame of the combustion chamber to the wall is being minimized. However, this is not being used very much nowadays, and whereas if you look at the coaxial atomizer, in which case like the oxygen, this is your oxygen will be passing through the central hole, and these two are fuel is the coaxial, and this is being used very much particularly for cryogenic engine. And in this case you can have without any recess, or in this case generally the fuel will be in gas phase and which will be coming in a very high velocity, let us say order of something 300 meter per second, whereas oxidizer will be passing through this central thing maybe order of something around 30 meter per second, which is, and in some cases that is being used, the recess is being used, so that there will be some zone, this let us say I am extending this portion, there will be some kind of gas which will be mixing out, and then it will be impinging little bit into the liquid jet which is coming out from this orifice, and as a result the mixing will be better, and then it may be atomization will be better, and the length requirement for this kind of atomizer leading to the complete combustions and vaporization, atomization is very much reduced. As a result, this is being used nowadays particularly for cryogenic engine and semi cryogenic engines, and however it is little difficult to manufacture, because this is your oxidizer and this is your fuel stream, and it should be centered properly, or a coaxiality should be maintained. However, when you use this recess, this is known as recess, a place in which the fuel and oxidizer are mixed, then the problem of common center need not to be that critical. And another thing which is being used is that is a Shrill atomizer. This is your Shrill atomizer, and in this case the tangential velocity, the V t is being, this is your tangential velocity is imparted to the liquid, such that instead of coming straight, so this will be having a cone over here, and this cone angle is varies something around maybe 70 to the 120 degree, and this angle is a very big. As a result, the liquid sheet, or this is the liquid cone is being formed and then thinning out, and then there is a this will be shredding will be taking place, and the distribution will be very good, and it will be occurring at a very shorter distance from the exit of this atomizer. Keep in mind that the tangential velocity can be imparted by various ways. One can use a screw, one can use a tangential entry, this is your tangential entry, entry, and it can be also swirler can be designed with a proper angle of swirling angle, so that it can have a very good spray. And keep in mind that this spray cone angle angle will be decided by the amount of swirl angle is provided in that. So, this is being used very much nowadays, but and it can be used along with this coaxial atomizer. It can be like, let us say for example, like oxidizer can be one way of clockwise rotation, the fuel can be anti-clockwise or it can be both. So, all permutation combination can really can be used for designing coaxial swirl atomizers. And as I told earlier, these are the three non-impinging atomizers which are used for non-hypergolic propellant. For hypergolic propellant, generally impinging type being used, and the one example is a doublet, in which case the fuel and oxidizer are impinging to each other. Keep in mind that this impinging is very important impinging point. This is your impinging point, and generally the oxidizer and will be flow rate will be much higher as compared to the fuel flow rate. So, if we use the same size of orifice for both, then naturally this impinging point will be not at the same center geometrical point, but rather it will be swayed away by because of fact that the velocity of oxidizer will be higher as compared to the fuel. So, that part has to be taken. So, if impinging point is not at the desired location, then the spray will be lopsided and then it may not really lead to the good atomization. In order to overcome these problems of impinging atomizers, there are two ways of doing it. One is the triplet. In case of triplets, what is being done that the fuel will be coming in center, oxidizer will be coming in at the periphery, it will be impinging. So, that anyway fuel is entering into here, and this is does not matter where this, whether it is impinging nearby or not, the fuel is always there and then one can avoid. The problem will be a little severe if the impinging point is really very lopsided. And keep in mind that this doublet and the triplets atomizer are basically used for hypergolic propellant. And if you want to have another solution to overcome this problem of swayed away of impinging point by the one of the stream, that is the splash plate. So, what you do, you basically use this plate, and which is being used as that even if it is swayed by this, and it will go and hit this plate and then disintegrate it into the droplets, and then so that you can really have a better spray or better distribution of droplet. But problem with this kind of thing that you can only towards the wall, and then there might be a recirculation zones which may affect that thing, and as we know that the fuel should be near the wall region, so that it should be acting as an insulating layers, and beside this the oxidizer should not come in contact with the high temperature wall, so that it will be getting eroded. And beside this, if some of these fuel oxidizer mixtures will be ignited, and then it may lead to the little high pressure in this zone and lead to the explosion, provided it is not properly managed. So, therefore, the splash plate atomizer, the injector is not being very much used, and beside this the pressure losses will be very much higher due to the presence of this plate, and also structurally it will be little weaker in that sense, because this plate will be subjected to very high temperature and pressure gases. And beside this, the other one which is being used for the non hypergolic propellant, that instead of using this the impinging of the fuel and oxidizer, the fuel and fuel can impinge together here, and similarly oxidizer and oxidizer both the stream can be impinging from the manifold of oxidizer, and such that one can have, this is known as the like impinging, like stream impinging, and this is known as the unlike propellant impinging doublets. So, if you look at these are the things what should keep in mind under various applications one can think of, and note that this diameter of this orifice is really very important, and also the number of orifices what will be really used, that we will have to see, and the what is the manifold and size and how this has to be designed we will see. And let us now look at how to we can analyze these typical atomizers, and that we will have to see. And we know that let us say there is a rocket engines, right. And in this case the let us say the liquid is coming through, this is your oxidizer and this is coming through the fuel. This is a coaxial injectors, this is the coaxial injectors, and we are looking at single, and it is having this is your nozzle, and it will be producing some thrust because of combustion which will be taking place here. And we need to look at how what is the mass flow rate of this propellant, and then passing through, and then what will be the fuel oxidizer ratio, and how we can find out diameter of the injector or the orifice. So, for that we will have to look at the mass flow rate of total propellant. You can say this is basically m dot p to total propellant, and that is basically nothing but F is your thrust, that is your thrust, and this is your V exit velocity, right. This is your V E, right, exit velocity. Of course, we are assuming this as a coming as a, and m dot is the total mass flow rate of the propellant, which consists of the mass flow rate of the fuel and mass flow rate of oxidizer. And if I will divide this thing by the mass flow rate of fuel, this is your basically mass flow rate of fuel, and we will get this as a mass flow rate, and this is equal to 1. And if I can define this as a mass ratio, that is the mass ratio or we can say the mass flow ratio then I can get basically m dot f as I can write down here m dot f is m dot divided by 1 plus m r. So, that we can write down as m f is nothing but your 1 over 1 plus m r into m dot, and similarly from this we can get the m dot oxidizer is nothing but your m dot f into m r. So, I will get m dot oxidizer equal to m r divided by 1 plus m r into m dot f. So, if I know the any one of them mass flow rate, and if I know the mass ratio or the fuel oxidizer ratio, we can say this is basically m r. I can say this is oxidizer fuel ratio, right, oxidizer fuel ratio. So, then we can really calculate what will be the mass flow rate of oxidizer and what will be mass flow rate of the fuel. So, by applying the Bernoulli's equation across this injector, if I consider this as a injector. So, this is your injector, let us say, and it is connected to a manifold which is having pressure P T, and this is the velocity what I am getting V, let us say this is your oxidizer, right, and this is oxidizer manifold. So, and the pressure which will be there, this is your static pressure. So, by applying the Bernoulli's equation to this injector, I can get P t is equal to P plus half rho V square, and this rho is basically the density of the propellant, or it can be oxidizer, it can be fuel, it can be anything. So, then I can write down this basically V is equal to 2 P t minus P 1 divided by rho, and this is nothing but your delta P is your the pressure drop across the injector. Delta P, the pressure drop across the orifice. And for real flow, the losses like contraction, kinetic energy fractions and flow separations extra can occur, because this is an ideal equations, and Bernoulli assume that there is no viscosity where there is no separation. But in actual situation there might be separation, there might be certain losses due to friction, and then we can modify our equation, that is this equation, let us say this is equation 1, and by using a factor that will be writing, that is basically a factor the discharge coefficient, and this is we call discharge coefficient. And this is of course, we know that Q dot is the flow rate is nothing but your A into V. So, by using that we can write down the flow, that is basically Q dot is volumetric flow rate this is your Q dot, and is alpha divided by root over 1 plus zeta into A I. A I is the injector's cross sectional area, it can be oxidizer, it can be fuel, root over 2 delta P by rho, and of course, these together we call it as a C D. Keep in mind that this alpha is the coefficient of contraction, zeta is the relative value of kinetic energy loss, and delta P is the pressure ratio across injectors, and A I is injection area or injector's cross sectional area. This is injector cross sectional area, and C D is the discharge coefficient, and generally the C D will be so that we will have to get from the experimental data, and m dot is nothing but rho into Q dot, which is rho C D A I root over 2 delta P divided by rho. If I take this rho inside, I will get m dot, that is the mass flow rate, is equal to the C D A I root over 2 rho delta P. And of course, for a multiple injector, multiple injectors, the mass flow rate would become basically you multiplied what are the number of the injector, that is m dot is equal to n j into C D A I root over 2 rho delta P, and this is the number of injectors or the orifices whatever we are having, right. So, that you can just multiply it, and then by knowing this we can get this MR, that is oxidizer to fuel ratio. I can get is basically m dot oxidizer divided by m dot f is equal to n oxidizer CD oxidizer AOX divided by NF CD of the fuel and AF, and of course, this is the in the numerator root over 2 rho oxidizer delta P x divided by the root over delta F delta P F. So, you can see that this is basically one has to know the what is the change in the pressure across the oxidizer stream and the fuel stream, and you should know also the CD of oxidized stream and everything, and if I also the area ratio. But if I know this MR, and I can find out by assuming one of them and then getting that value. So, we will be taking an example in the next lecture to see how we can calculate the diameter of the oxidizer, and with this I will stop over, and thank you very much.